Hi, this is Ken Johnson for another episode of SecCast. In this tutorial, we discuss and demonstrate cross-site scripting, also known as XSS. First, we will discuss and explain the concept of XSS. Then, we will demonstrate manual and automated techniques for discovery and exploitation. Finally, we will discuss prevention. Let's get started. Cross-site scripting is known as XSS or HTML injection. The concept is pretty clear and concise. You provide some data to the application, and the application returns that data in either a safe way or unsafe way. If done unsafely, you can inject your HTML, JavaScript, or CSS code into existing HTML, JavaScript, or CSS code on the page. When you can change the look, feel, and behavior of an application, there are clearly some malicious consequences to doing this in an unsafe way. We will demonstrate the impact during this tutorial. It is important to know that there are three primary methods of XSS: stored, reflected, and DOM-based. Stored cross-site scripting means that the data you provide to the application is first stored somewhere such as a database, file, or caching server. Later, that data is retrieved and unsafely rendered to the user. Reflected XSS occurs when you provide data to the application and that data is not stored anywhere, but instead is immediately reflected back in the response and then lost from the application's memory. Think of it like catching a ball and then throwing it right back. DOM-based XSS occurs when an unsafe attribute of the DOM is pulled out and placed into existing client-side code without safeguards, think HTML or JavaScript, and executed by the browser. The first thing we would like to demonstrate is the simplest form of testing for cross-site scripting. We are going to enter in JavaScript code that, if rendered back unsafely, will be executed as application provided code and allow us to display an alert box with the number 1 inside of it. We will enter the JavaScript into the first name field. Upon submission and completion of the request, we will hit refresh to see if our code executes. The code does indeed execute, as evidenced by the alert box. Let's take a peek into the page's client-side source code to see what is going on. First, let's inspect the welcome section of the header. When we navigate down into the code, you can see our JavaScript placed onto the page and executed as if it were valid JavaScript. Instead, these values should be safely HTML encoded, but they are not. Next, let's take a shot at performing some automated detection and validation. We want to leverage the tool XSS Validator. XSS Validator is hosted on GitHub and is updated more frequently on GitHub than in Burp itself, so instead of using the plugin available in the Burp App Store, we are going to download the latest version and use that. XSS Validator essentially creates payloads that can be used in tandem with a running headless web browser to verify that JavaScript is executing. When successful, you will see a response that has the unique identifier generated by XSS Validator in the response. Following the instructions available via the GitHub page, we navigate to the HTTP components library, choose the download section, and download the HTTP components binary, or compiled files. Next, we open up the HTTP components folder we've just downloaded, copy the jar files located under the lib directory, and paste them into the burp extender /lib directory. Next, we navigate to the burp extender bin burp directory and run the command ant to build the code and create our XSS Validator jar file. You can see that the build was successful, and after running an ls command, we can see that the XSS Validator.jar file is available now. We will navigate back to directories and change directories into the XSS detector folder. We start PhantomJS using the XSS.js file. It is important to note that you can use a package manager such as brew or apt to install both ant and PhantomJS. Next, we open the extender tab on burp and add a burp extension. We'll choose the XSS Validator jar file. Once this is loaded, we'll go back to our HTTP history and forward the original request to update our profile onto Intruder. Next, we'll highlight the field we want to test, in this instance, the first name field. Next, we'll choose our payload and select extension-generated payloads. Now we select XSS Validator and click OK. We will also navigate to the grep match field on the Options tab. We need to clear out the existing patterns. Next, we will navigate to the XSS Validator tab and copy the grep phase value. We paste this value into the grep match column, and the flag result option is automatically checked for us. Time to start the attack. After running, we look for responses that have grep field value checked and pinpoint 200 responses, since these are pages that responded normally and appeared to be vulnerable, as the unique identifier placed in the grep field are returned in the response. After opening up the request and response, we review the response and see that we were able to inject the unique value into the response, indicating the response came back with our XSS validator payload intact and executed in the PhantomJS browser. This is a vulnerable request. Let's clean it up and take a look. You can see that we have some JavaScript that writes the unique identifier to the DOM's logging feature. This means our attack was successful. Now, just because your JavaScript does not execute does not mean that the application is safe. I'll show you two examples of this concept. Once again, we open up the request to update our profile. However, this time we will send the request to repeater. We enter the generic XSS payload into the first name field. Note that the application returns the JavaScript in full. Now, the developers have implemented a fix and would like us to test the function. We send the request again, and this time we can see our script tags have been removed. Note that if the response is being placed directly into JavaScript, that is to say, between JavaScript script tags, this hasn't really fixed anything, since we don't need to inject script tags for our code to execute. However, for the sake of this conversation, we will say that we do in fact need script tags. Now, if the script tags are not being removed recursively, that is to say, if a substitution method is not repeatedly removing patterns, in this case script tags, until there are none left, we may be able to place script tags within script tags so that when the first script tag is removed, the next script tag becomes fully formed and is returned unsafely and executed. So we place fully formed script begin and end tags within the first name field. We see that the substitution operation is not occurring recursively, so we are able to bypass developer implemented protections. Also keep in mind that uppercase script tags work as well, so if the pattern is only checking for lowercase script tags, the operation will fail to protect the application. There are a lot of ways that one could potentially bypass XSS protection, so familiarize yourself with the various tools, techniques, and bypass cheat sheets available on the web, as well as stay tuned for our advanced web hacking series. Exploitation is important in terms of showing the value of XSS. We will once again show the generic alert box example. This example, while it does effectively demonstrate that your injection of HTML or JavaScript is technically possible, may not sufficiently provide context with regards to impact. Next, we go a step further with demonstrating real-world impact. In this example, we fire up our Python web server on local port 8000. We enter document.location and the location of our web server, along with string concatenation of the URL and the user's cookie. Because the cookie is not protected by an HTTP only flag, once the user visits this page, they will be redirected to HTTP localhost port 8000 / their cookie value. After submitting and then refreshing the page, we look at our simple web server's log. We can see that a request to our web server took place, and now we have the user session cookie. This means we can authenticate to the application as that user. The last example of exploitation will be demonstrated using the Browser Exploitation Framework, or BEEF for short. BEEF is a tool dedicated to leverage XSS vulnerabilities to compromise a user's account, computer, or generally have some fun. Following the instructions, we will copy the git clone statement and run git clone so that we can download the repository. Next, we change into the BEEF directory and type bundle which reads the project's gem file and installs all the libraries necessary to run the tool. Once this is all completed, we fire up Beef. First, we navigate to the browser UI and enter in the default credentials, username Beef and password Beef. Next, we enter in JavaScript into the first name field intended to redirect a user to the demo page provided by Beef. We hit refresh, and we are redirected to the demo page. Next, we select our victim browser. Firstly, to verify and demonstrate that we are hooked properly into the browser, we will execute some JavaScript on our victim's browser. You can see that we managed to open alert box with SecCast tutorial inside of it. Next, we will select Browser Webcam. Change the time from 1 second to 3 seconds for personal preference and click Execute. Our victim must accept this plugin. Once they do, our code begins capturing screenshots. Next, we will open the Beef database and navigate to the core results table. We will copy the content of one of the results and paste it into the test.txt file and remove the data that is irrelevant. We will simultaneously decode the contents of this file and output them to a test.png file. Finally, we open the test.png file and can see that we have taken a screenshot of ourselves. This demonstrates real-world impact to privacy and demonstrates the power of an XSS vulnerability. When discussing prevention, and much like SQL injection, you often hear people say, sanitize input. This can be somewhat of a cat and mouse game. You may filter certain inputs but forget others, and developers should never underestimate the cleverness of attackers. Alternatively, I'd like to recommend HTML encoding, preferably with a popular library or framework that can do this heavy lifting. HTML encode means that characters considered to have JavaScript or HTML context, such as the greater and less than symbols, are encoded so they are not considered code but rather text that should be displayed on the page. To demonstrate this, we enter in the alert box JavaScript code and review the response. In the response, you can see that our code is rendered as exactly that, code. It will be interpreted and executed by the browser as such. Now, we've used the protection our framework provides to HTML encode this output. Let's submit again and review the response. Firstly, note that the alert box does not actually pop up. If you look in the client-side source code, you can see that the greater than and less than symbols are HTML encoded and are not interpreted as code, but rather text. Remember that JavaScript libraries should be kept up to date as they may contain vulnerabilities where previously benign or HTML encoded data is then HTML decoded and placed into the page, allowing the data to execute as code. Okay, so to recap, we've discussed manual detection, automated detection with XSS validator, and demonstrated simple bypasses for XSS filters. We demonstrated exploiting Crosssite scripting through the theft of screenshots taken from our victim's browser. And finally, we've briefly discussed preventative measures. I'm Ken Johnson. This has been another episode of SecCast. Thanks for watching.